Okay, let's unpack this. We usually picture algorithms as, lines of code inside computers, guiding our Netflix or our GPS.
Right. Running our devices.
But think bigger. Have you ever considered that shaping a Stone Age tool, those
Yeah.
precise strikes, that was basically an algorithm?
Or following a recipe, yeah.
Yep.
Or a knitting pattern. It's just a defined sequence of steps. They're way more fundamental than just tech.
Exactly. And this isn't just about the algorithms humming away in our phones or whatever. Today, we're diving into what one of our sources calls human algorithm design.
Uh-huh. It's about seeing how these computer science principles can offer, well, fresh perspectives on everyday puzzles.
Yeah.
The ones you actually face.
Yes. And the material we've been looking at covers a really surprising range of stuff that I know listeners want to get their heads around quickly.
Things like optimal stopping.
Right, like when's the best time to make a decision and explore exploit.
How to balance trying new things versus sticking with what works.
And also, smart ways to organize your life, your work, your time, these universal challenges.
And what's really interesting, I think, is that computer science, in tackling these incredibly complex problems, has found some insights that, well, they kind of challenge our usual ideas about being rational.
They really do. These aren't your typical, straightforward self-help tips.
No. We're talking about ideas like maybe you don't always need to check every single option.
Or that sometimes good enough is genuinely the best you can do.
Making a bit of a mess can actually help sometimes. Traveling light mentally, too.
Trusting your instincts, yeah. And even, believe it or not, flipping a coin can sometimes be a totally valid strategy.
It's a whole collection of kind of counterintuitive wisdom.
So what's the mission today? What are we trying to do here?
Well, I think the core idea is to pull out the essential takeaways from this material. Give you not just tips, but maybe a new vocabulary, a new way to think about the world, and even yourself.
Okay, great. Let's jump into one of these really fascinating areas then. Optimal stopping.
Good place to start.
And maybe the best way in is the classic secretary problem. Have you come across that?
Oh, yeah. It's a standard. You're interviewing candidates one by one.
Right. And once you say no, they're gone. You can't go back. The goal is to hire the single best person out of the whole pool.
And what's pretty wild is that even if you use the absolute mathematically best strategy, you'll still fail to pick the very best applicant. Something like 63% of the time.
Ouch. 63% failure rate. As one source points out, that's maybe not super encouraging if you're applying it to, say, finding the one.
Right. A bit grim for romance.
But here's where it gets really counterintuitive, I think. Your gut might say, well, if you have way more applicants, a huge pool, your chances of finding the absolute best one must go down.
Yeah, bigger haystack, harder to find the needle. Seems logical.
But the math says no. If you use the optimal strategy, your probability of picking that single best person actually stays constant, right around 37%. Doesn't matter if it's 100 applicants or 1,000,000.
Which is amazing. So the bigger the pool, the more valuable knowing that optimal algorithm actually becomes, even though you're still, statistically more likely to miss the number one choice.
Okay, so that's hiring, which is maybe a bit abstract for some. How does this connect to something more everyday, like finding a parking space?
Ah, the parking challenge. It's a great analogy. Think about all the factors. The cost, obviously, if it's a paid spot.
The walking distance, the hassle.
Exactly. The time you spend circling, the gas. And it all changes depending on your situation, right? If you've got passengers, maybe you'll pay more for closer, but the searching still frustrates everyone.
And it's not just you versus the lot, is it? There's this, game theory element with all the other drivers doing the same thing.
Definitely. And a key metric that dictates everything is just the occupancy rate. What percentage of spots are full? Low rate, easy parking. High rate. Well, we've all been there.
Now, one source brings up this idea I really liked, always be stopping, and connects it to these great quotes. Stephen Grellett, I expect to pass through this world but once. Let me do it now. And Annie Dillard, more direct. Spend the afternoon. You can't take it with you. It's about seizing opportunities when they arise.
Yeah, don't wait indefinitely for the perfect moment that might never come. Which brings us back to the core question from optimal stopping.
Do we actually do this? Do humans intuitively follow these optimal strategies when we're looking for jobs or partners or apartments? Do we kind of know when to stop looking and commit?
That's the million-dollar question, isn't it? How close does our intuition get?
Definitely food for thought. Okay, next up. This explore-exploit dilemma. This feels like something we're doing constantly every day.
Oh, absolutely. It's this fundamental balancing act. How do you decide when to try something new, explore, versus sticking with something you know is pretty good exploit?
Like choosing a restaurant, yeah. Old favorite or the new place down the street.
Exactly. And this is actually a core problem in computer science, too. They call it the multi-armed bandit problem.
Right, like a row of slot machines. Each pays out differently, but you don't know how.
Precisely. And you want to figure out which levers to pull, in what order, to maximize your winnings over, say, 100 pulls.
So how do you solve that?
Well, for cases where you know exactly how many pulls you have in total, a guy named Richard Bellman worked out an exact solution. It involves working backward from the very last pull.
Working backward, that sounds complicated.
It can be, yeah. You figure out the best choice for the last pull, then the second to last, considering what might happen, and so on, all the way back to the first pull.
Okay, maybe a bit much for choosing dinner. Is there a simpler way to think about this trade-off?
There is. One approach is something called the Gittins index. It tries to put a numerical value on each option, each arm of the bandit, even the ones you know nothing about.
A value on the unknown. How?
And here's a really interesting bit. An option you know nothing about can actually have a higher Gittins index seem more attractive than an option you know is, say, pretty good, maybe pays out 70% of the time.
Wow. So the mystery factor, the potential, can actually outweigh a known good thing.
Exactly. There's this sort of exploration bonus. As you try an option and find out it's just okay, maybe 50-50, its Gittins index will eventually settle down near 0.5. But initially, that bonus is powerful. Even one failure doesn't necessarily kill its appeal right away.
That makes a lot of sense, actually. We're often drawn to the new, the possibility. Our source also mentions upper confidence-bound algorithms, UCB.
Right, UCB algorithms. Similar idea, assign a score. But instead of just expected value, UCB focuses on the optimistic potential. It chooses the arm that, based on what you know now, could reasonably turn out to be the best in the future.
So back to the restaurants. A new place, even with mixed reviews, still could be amazing.
Exactly. As long as you haven't tried it enough times to be sure it's mediocre, its potential keeps its UCB score high. It prioritizes the upside possibility. Often gives similar results to Gittins, but can be easier to calculate.
Got it. And this explore-exploit thing, it feels like it's everywhere online now with A/B testing.
Oh, massively. A/B testing is pure explore-exploit. Show version A to some users, version B to others, see which button color, which headline gets more clicks or signups.
Like the Obama campaign example, right. Optimizing their donation page.
Yeah, that was a famous early case. Reportedly brought in millions extra, led directly to companies like Optimizely being founded, which then worked for both campaigns in 2012. Now, almost everything you see online, colors, images, text, ads, is likely being constantly tweaked by these algorithms.
Who are the guinea pigs?
In a way, yeah. In that multi-armed bandit scenario, our clicks are the payout the algorithm is trying to maximize. Just to be clear for listeners, A/B testing is just running a controlled experiment online. 2 versions, see which works better.
It's kind of wild to think about. The source also makes a really interesting point comparing this to clinical trials for medicine.
It does. If you think about it, the standard clinical trial design, dividing patients into groups, one gets the new drug, one gets a placebo or standard care. For the whole trial, it functions a lot like an A/B test.
The goal is finding out which treatment is definitively better overall.
Right. Rather than necessarily adapting during the trial to give more patients the treatment that seems to be working better within that trial. It raises complex ethical questions about balancing research goals with individual patient well-being during the study itself.
That's a heavy point. Okay, one last thing on explore-exploit. This idea that humans tend to over-explore.
Yeah. The Tversky and Edwards experiment from the 60s, they had people watch 2 lights flashing, each with a different hidden probability. People could either watch which light came on or bet on which one would come on next. And people consistently spent more time just watching and exploring than the math said was optimal for maximizing their score, even when the probabilities weren't that close. It seems we have this inherent curiosity. We want more data, even if it's not strictly the most efficient path to the reward.
Ah, sounds familiar. Okay, let's switch gears. Sorting. Seems mundane, right? Putting things in order.
You'd think so, but it's incredibly fundamental. The source uses merge-sort and sorting books as a nice relatable example, taking that messy pile and systematically getting it ordered.
And then these huge book sorting places like Preston Sort Center competing with the New York Public Library on speed. That's amazing.
It's industrial scale sorting. And the key point the source makes is about the cost unsorting. It's inefficiency, especially if you know you'll need to find things again later.
Makes total sense. A messy desk versus an organized one, or finding a file on your computer.
And the ultimate example of sorting's power, Google.
How do they search the entire web in like half a second?
Well, they don't actually scan the live web for every search. That'd be impossible. They do massive amounts of pre-sorting and indexing of web pages beforehand. So when you type your query, they can jump almost instantly to the relevant pre-sorted results.
Ah, so the upfront work of sorting pays off massively with every single search. Okay. But the source also points out that sometimes doing lots of comparisons, which is what sorting involves, isn't necessarily bad. Like in sports, baseball's long season.
Right. A computer scientist might look at thousands of baseball games and say, why not use a more efficient tournament bracket to find the best team faster?
Yeah, why play so many games?
Because in sports, the games themselves are often the point. It's not just about efficient ranking. The process, the season, the narrative, that's the entertainment.
That's a great distinction. The journey matters, but then compare that to something like high-stakes cash game poker.
Yeah, a totally different world. In cash games, where people are playing with real money hand after hand, the most critical skill isn't just being a good player. According to top players like Isaac Haxton, it's accurately judging your own skill compared to everyone else at the table.
Knowing where you rank in that specific group?
Exactly. Because if you're not truly world-class, playing against the very best will just drain your money. So self-assessment, knowing your place in the sort, is absolutely vital there.
Fascinating. The source also uses the marathon as this incredible example of large-scale human sorting.
Think about it, tens of thousands run, and in hours, they're perfectly sorted by time. It's a massive sort operation, way faster than trying to rank them all through head-to-head matchups. A race is different from a fight, as the source says. It's about performance against a standard.
And this whole idea of sorting, it extends beyond sports, right? Into society itself.
Yeah, the source argues it's crucial for large societies. We use quantifiable metrics for status, money obviously, but even things like respect your elders uses age, a quantity.
Or GDP for nations.
Right. And even if these metrics are crude or imperfect like GDP, just having a shared benchmark transforms status from something potentially needing conflict to resolve into, well, just looking it up, it reduces friction, saves time, maybe even lives.
Wow. So even imperfect sorting helps maintain order. Okay, let's move to another core computer science idea. Caching.
Right, caching. The basic idea is pretty simple. Keep stuff you need often in a place where you can get it really quickly, like a small, fast bit of memory.
Where did this idea come from?
The source traces it back to early computers like Atlas and Maurice Wilkes, realizing you could use this faster memory to kind of anticipate what the computer would need next.
And the analogy the source uses is great, turning a library inside out.
Yeah, imagine that staff-only area in Berkeley's Gardner Stacks. It's like a cache full of recently returned popular books, the ones likely to be checked out again soon.
So instead of immediately reshelving them deep in the stacks,
Just make them available right there in the lobby. People grab them instantly. Staff saves shelving time. It's a shortcut. Win-win.
that's exactly what caching does. And this happens all over the internet, right? With companies like Akamai.
Oh yeah, Akamai is huge. They handle a massive chunk of internet traffic. They're essentially caching popular website content videos, images on servers, physically closer to users around the world. So things load faster for you.
Like a global internet lobby with the most popular stuff ready to go. And this isn't just digital, right? Amazon does this physically.
That's right. They're patent for anticipatory package shipping. It's like a physical cache.
Yay.
They predict what people in a certain area will buy and ship it to a local warehouse before anyone even orders it.
So when you click buy, it's practically already at your doorstep. That's incredible.
It really is. It's all based on predicting future needs. Which ties into why caching works in the first place, the idea that some information is more likely to be needed again soon.
Like Ebbinghouse's work on memory, the forgetting curve.
Exactly. Ebbinghaus showed we forget things over time. Information has a kind of half-life. What's relevant now might not be next week. So effective caching relies on constantly guessing what's most likely to be needed soon. It's time sensitive.
So it's dynamic. Bring things close when they're hot. Let them fade back when they're not. Makes sense for computers, and maybe our own brains too. Okay, let's tackle scheduling. Oh boy.
Yes, scheduling. The source opens with that powerful Annie Dillard quote. How we spend our days is, of course, how we spend our lives. really sets the stakes.
It does. And the story about the guy trying to write the definitive book on scheduling theory for 15 years and still not finishing tells you how hard it is.
We all know that feeling, right? Blank calendar, huge to-do list, dependencies, deadlines, urgent stuff, important stuff. It's overwhelming.
And people like Taylor and Gantt, they gave us tools to visualize schedules, like Gantt charts.
Right, helpful for seeing the plan, but they didn't really solve the core problem.
Right.
What is the optimal schedule? The first big mathematical step was Selmer Johnson in 1954.
And he used laundry as his example, washer then dryer.
Exactly. Different loads, different wash-dry times. How do you order them to finish fastest? A simple, relatable version of a complex problem.
But it gets way trickier, like that Mars Pathfinder issue, priority inversion.
Ah, yes. The classic example. A low-priority task grabs some resource, like a shared piece of data. Then a high-priority task needs that same resource, but it has to wait.
And while the high-priority task is stuck, medium-priority tasks just keep running.
Exactly. The most important job gets stalled by the least important one, indirectly. It's like Mitch Hedberg's joke about someone blocking a fire exit. Loitering shouldn't stop people escaping a fire.
Great analogy. So how do you fix that?
One solution is called priority inheritance. If that low-priority task holding a resource temporarily inherits the high priority of the task that's waiting for it, the system is more likely to let the low-priority task finish quickly and release the resource. The loiterer gets motivated to move.
Clever. Okay. The source also mentions Lawler and the shortest processing time algorithm.
Right. Generally, doing the quickest tasks first,
Yeah.
shortest processing time, or SPT, gets the most tasks done in the shortest overall time. It maximizes throughput. But Lawler found that as soon as you add precedence constraints, task A must finish before task B can start. There's no simple tweak to SPT that guarantees optimality anymore. It breaks the easy solution.
So dependencies just make everything harder. Seems right. And there's usually this trade-off, isn't there? Responsiveness versus throughput.
Always. Think about your computer multitasking. If it tries to give every single app a tiny slice of attention constantly so they all feel responsive, it might spend all its time just switching between apps, context switching, and not get much actual work done overall.
So being too responsive kills overall productivity.
It can, yeah. Sometimes letting tasks run a bit longer without interruption, even if others have to wait slightly, actually gets more done in total. Counterintuitive, but true, slowing down to speed up.
Like the saying, slow is smooth, smooth is fast. The source also talks about interrupt coalescing. What's that?
Okay, so interrupts are signals telling the processor, stop, deal with this now. Too many interrupts, like too much context switching, is inefficient. Interrupt coalescing is basically batching them up. Instead of interrupting for every tiny thing, wait a bit, gather a few requests, and handle them together.
Like Peter Norvig realizing he should run all his errands downtown in one trip, not multiple separate ones.
Exactly. That was his one-line bug in his personal scheduling algorithm. Grouping similar tasks reduces the overhead.
And the postal system kind of does this for us naturally, right? Mail comes once a day.
Precisely. It forces a batching process. You deal with mail once. It minimizes interruptions compared to, say, constant email notifications. It's free interrupt coalescing.
I like that. Okay, shifting again. Making predictions. We do this all the time, often with very little information.
Yeah, the source uses examples like when do you introduce a new partner to the family? How much should you save for retirement? Big decisions based on guesswork about the future.
And we don't usually have huge data sets for these personal things. It's not like Peter Norvig's unreasonable effectiveness of data. It's often small data.
Right, like that story about gut predicting divorce rates from just watching couples interact for a few minutes. Sometimes you have to infer a lot from a little.
And when we do have data for things, it often follows these weird distributions, right? Power laws.
Yeah, power law distributions, think town populations, lots of small towns, a few medium cities, and then a tiny number of massive metropolises like New York or Tokyo, or movie grosses, tons of flops, some modest hits, a few blockbusters.
A lot's below average, a few way, way above.
Exactly. And this is super important for things like income or wealth, which also tend to follow power laws. The average income can be really misleading because most people earn less than that, but a few billionaires pull the average way up.
So the average isn't typical at all. How does this compare to other situations, like gambling?
Well, the source contrasts power laws with things like normal distributions, like human height, or memoryless distributions. A memoryless process, like roulette spins or coin flips, means past results tell you nothing about the future. Each spin is independent.
So Kenny Rogers was wrong. Know when to hold 'em, know when to fold 'em. Doesn't apply to roulette.
Not really, no. In a truly random, memoryless game, there's no do, win, or hot streak that statistics supports, which, the source suggests, might actually make those games more addictive, because there's never a statistically right time to walk away based on past results.
That's an interesting, dark thought. But the source also says our intuitions are sometimes surprisingly good, like aligned with Bayesian reasoning.
Yeah, even for things without public data, like predicting customer service hold times. Researchers looked at how people update their predictions as they wait longer. People seem to implicitly use a multiplicative rule. Like, okay, I've waited 5 minutes. I now expect the total wait to be maybe 15 minutes. Then after 10 minutes, maybe they expect 30 total. This pattern is consistent with assuming the underlying waiting times follow a power law distribution where long waits are possible.
So our gut feelings kind of reverse engineer the likely distribution. That's cool.
It is, but there's this tension the source points out. When we talk to each other, we focus on the unusual, the outliers, the dramatic stories.
The exceptions, not the boring averages.
Right, and the news, social media, they amplify this massively. It makes it harder to maintain accurate baseline assumptions or priors in Bayesian terms about how common things really are. We get skewed by the memorable exceptions.
Yeah, the narrative overrides the statistics sometimes. Okay, let's talk about overfitting. This sounds technical, but it seems really relevant.
Definitely. The source starts with Ben Franklin listing pros and cons his moral algebra. Darwin did something similar deciding whether to marry. The idea is, consider more factors, make better decisions.
Seems reasonable. More data, better model, right?
To a point. Think about drawing a curve through data points. With more factors, you can make the curve bendier, fitting the existing points perfectly.
What's wrong with that?
The danger is overfitting. You fit the data too perfectly, including all the random noise and quirks specific to that data set. Your model looks great on the data you use to build it, but it fails miserably when you try to use it on new, unseen data.
So it learned the noise, not the underlying pattern.
Exactly. The source uses a great phrase, praying to the bronze snake of the data, not understanding the real forces. It mistakes the specific data points for the general truth.
Can you give a real-world example?
Well, the source points to things like training scars in high-stress professions, military or police training drills, specific actions over and over.
Okay.
But sometimes those ingrained actions become counterproductive or dangerous in a real situation that's slightly different. Like officers instinctively pocketing spent bullet casings during a real gunfight, totally standard on the practice range, useless or worse in reality.
Wow. Or the example of instinctively handing a training weapon back to the assailant, role player.
Yeah, horrifying to think about that reflex in a real confrontation. It's overfitting the training scenario.
Chilling. The source also uses rapidly changing food trends.
Right. Soy milk, almond milk, oat milk, coconut water, kale. Fads change so fast. A model predicting food sales based perfectly on data from 3 years ago would likely be totally useless today because the underlying data-generating process people's preferences has shifted.
So when things are uncertain or changing fast, trying to be too precise is bad.
It can be, yeah. The suggestion is sometimes you need to paint with a broad brush, like using a thick marker for initial brainstorming sketches. Don't get bogged down in tiny details before the big picture is right. Focus on robustness over pinpoint accuracy.
That makes sense. And this idea of relaxing a problem, like the traveling salesman.
Right. The traveling salesman problem, finding the absolute shortest route visiting multiple cities, is incredibly hard computationally. So you relax the rules. Maybe allow revisiting cities or flying instantly between them. This creates a simpler problem, like finding the minimum spanning tree connecting all cities.
Which doesn't give the exact answer to the original problem.
No, but it gives you a useful bound. The true shortest route can't be shorter than the length of that minimum spanning tree. It gives you a baseline, a starting point, without solving the impossibly hard version.
Clever way to handle complexity. And using randomness, like for testing polynomials.
Yeah, proving mathematically that two complicated polynomial expressions are always identical is hard, but you can just plug in random numbers for the variables. If you get different results even once, you know they're not identical. Do it a few times with random numbers, and you become extremely confident, even without a formal proof. It's a probabilistic shortcut.
Using randomness to get good enough certainty quickly. And Monte Carlo methods for policy.
Similar idea. Evaluating the full impact of something complex like healthcare reform on every single person is impossible. So, Monte Carlo simulations use random sampling. They run the model many times with different random inputs representing population variations and look at the distribution of outcomes. It gives a richer picture than just one single prediction or anecdote.
Better than cherry-picking stories or relying on crude averages. Okay. And finally, Bloom filters and trading certainty for speed.
Right. Search engines need to track billions of URLs they've already crawled. Storing that full list is huge. A Bloom filter is a clever, compact data structure. You can ask it, have I seen this URL before? It can quickly say, definitely not, or possibly yes.
Possibly.
Yeah, there's a small chance of a false positive. It might say possibly yes for a URL it hasn't actually seen, but it will never say definitely not for a URL it has seen no false negatives.
So you trade a tiny bit of certainty, the small chance of a false positive, for massive savings in storage space and speed.
Exactly. A deliberate algorithmic trade-off, sometimes probably right, is much more useful than perfectly right, but too slow or too big.
Fascinating stuff. Okay, let's try to pull some of this together around this idea of the human algorithm.
Right. And a core concept here is blind variation and selective retention. James Campbell. The idea draws from evolution. Basically, creativity and learning happen by generating lots of variations, often randomly or semi-randomly, and then selecting the ones that work best.
Like those stories of Newton or Mozart feeling like ideas just poured in and their job was to pick the good ones.
Exactly. Less about methodical construction, more about recognizing and retaining the fittest ideas from a flow of variations.
So how do we apply that? The source suggests deliberately adding randomness, like the Wikipedia random article button.
Yeah. Or reading random blogs, trying random activities. Even if it just exposes you to weird stuff, it can broaden your perspective, maybe spark unexpected connections, calibrate your sense of randomness.
I like that. Shake up the routine. Another strategy mentioned is exponential backoff from early networking.
The Elohanet in Hawaii, yeah. If two computers transmit at the same time and the messages collided, they'd each wait a random time before trying again. If they collided again, they'd double the average waiting time before the next try, and so on. Exponentially increasing delays to reduce congestion.
And this has been applied in the justice system, the HOPE program.
Amazingly, yes. For probation violations, particularly drug use, instead of waiting for multiple failures before a big consequence, HOPE uses swift, certain, but initially small sanctions, like a day or two in jail for the first failed drug test. If it happens again, the sanction increases maybe a week. It applies that exponential back-off idea.
And it works.
The results reported are really impressive. Significantly fewer repeat offenses, fewer probation revocations compared to standard probation. Predictable escalating consequences seem effective.
Wow, from network packets to probation. Okay, what about TCP congestion control, that AMD thing?
Right, TCP. The protocol that runs much of the internet uses additive increase, multiplicative decrease. When things are going well, it cautiously increases its sending speed, additive increase. But if packets start getting lost, signaling congestion, it drastically cuts its speed back, multiplicative decrease.
Creating that TCP sawtooth graph you see sometimes?
Exactly. It's constantly probing for more bandwidth, but reacts sharply to signs of trouble. It's a feedback loop.
And the source contrasts this flexibility with something like the rigid Peter principle in companies where people get promoted to their level of incompetence and stay there.
Yeah, the idea being maybe organizations could benefit from more dynamic adjustments, like TCP. Maybe roles and responsibilities shouldn't be quite so fixed, allowing for quicker adaptation when things aren't working. More feedback, faster adjustments.
Interesting parallel. And this idea of feedback, it cropped up simultaneously in linguistics too.
Right around the same time, networking engineers were figuring out feedback for TCP. Linguists were realizing that conversation isn't just one person talking then the other, like Chomsky's idealized models. It's full of feedback nods, interruptions, what they call back channels. It's interactive.
So feedback is key everywhere. And in networks, when feedback fails or buffers get too big, you get tail drop.
Right. If a router's buffer, its waiting area for packets, gets completely full, it just starts dropping any new packets that arrive. Tail drop. It seems harsh, but it's crucial negative feedback to the senders. Slow down. The network is clogged.
Like a popular crepe stand having to turn people away when the line gets too long.
Perfect analogy.
Yeah.
And if the buffer is too big, it delays that feedback. Senders keep sending too fast for too long, leading to more overall delay. Sometimes smaller buffers and quicker drops are actually better for overall flow.
So dropping packets can be good.
Okay.
And Stuart Cheshire's point about latency versus bandwidth.
Yeah, he argued passionately that for human interaction online, Low latency meaning low delay. Quick response time is often way more important than just raw bandwidth, how much data you can push per second.
His Boeing analogy.
Right. A 747 carries more people than a 737, but they fly at roughly the same speed. For getting one person somewhere, the 747 isn't faster. Similarly, for a quick web search or a video call, minimizing delay is key, maybe more than having massive download capacity. Responsiveness matters.
Makes total sense. Okay, final stretch. Game theory. The prisoner's dilemma.
Classic example of how individual rational choices can lead to a collectively bad outcome. Two suspects interrogated separately. If both stay silent, they get a small sentence. If one rats out the other, the rat goes free, the silent one gets a long sentence. If both rat each other out, they both get a medium sentence.
And the individually rational choice is always to rat the other person out.
Right. Leading to both getting medium sentences, which is worse for both of them than if they'd both stayed silent. It applies to things like arms races or potentially climate change individual benefit from polluting versus collective harm.
And just changing the payoffs, like offering a bonus, might not fix it. The Evernote vacation example.
Exactly. Evernote offered cash to employees who took vacation, trying to change the payoff. But it didn't necessarily change the underlying game dynamics. People might still feel pressure to take less vacation to seem more committed than colleagues, even with the bonus. You often need to change the structure of the game, the incentives, not just tweak the rewards.
Got it. And algorithmic trading, does it make markets crazier?
It can amplify swings, certainly. High-speed algorithms reacting to each other can create feedback loops. But the source reminds us, humans are perfectly capable of irrational market bubbles and crashes all on their own. The problem is often the game structure itself, whether played by humans or algorithms.
Fair point. But there's encouragement for sticking to your guns, even if the herd is going elsewhere.
Yeah, the idea is, even if you're wrong more often by going against the consensus, when you are right, you might provide a crucial dissenting data point. You create a positive externality, maybe saving the herd from going completely off a cliff. It takes conviction, though.
Then there's algorithmic game theory considering the effort of thinking.
Right. Standard game theory often assumes players have infinite computational power to figure out the optimal strategy, including predicting what others will predict you will predict. It gets crazy. Algorithmic game theory asks, what if thinking is hard? What strategies work well when players have limited time or brain power?
Like the Vickery auction.
Perfect example. Highest bidder wins, but pays the second highest bid price. This clever structure makes the optimal strategy much simpler. Just bid your true value. You don't need to waste mental energy guessing what others will bid nearly as much. It reduces the cognitive load.
Makes the game easier to play optimally, which relates back to Sartre. Hell is other people.
Yeah. The source suggests maybe Sartre was onto something about interactions being nightmarish if you're playing the wrong game. But if you can find strategies or design systems, like the Vickery auction, that don't require constantly getting inside everyone else's head, maybe interaction doesn't have to be hell. Maybe simpler strategies are sometimes best.
Which leads to the final big takeaway, focus on the process.
Exactly. Focus on the algorithm, the process, which you can control, rather than fixating only on the outcome, which you often can't fully control. It's like Bertrand Russell said. The wisest act is the one calculated to be most likely to lead to a good outcome, even if by bad luck it doesn't.
A kind of computational stoicism. Except you can't control everything. Focus on making the best decisions with the information and tools you have.
That's the idea. And it even applies to designing physical spaces. Like a computationally kind parking garage with just one simple path in and out, it eliminates all the complex maneuvering and second-guessing of a traditional lot. Good design simplifies the game.
Right. Makes it easier to navigate.
Exactly.
Okay, so wrapping this all up, the big insight here seems to be that computer science, these algorithms, they offer this really powerful, sometimes really surprising lens for understanding and navigating just, well, life, everyday decisions.
Absolutely. And what's striking is how often the best algorithmic approach feels counterintuitive compared to what we might initially think is rational.
And hopefully, for everyone listening, thinking about these concepts, optimal stopping, explore exploit, sorting, caching, scheduling, overfitting, feedback loops, game theory might spark some new ways to approach the challenges and decisions you face.
Which leaves us with a final question to maybe chew on. As algorithms become more embedded in our technology and society, how can we become better designers of our own human algorithms, our own strategies, our own processes? How do we make ourselves run more effectively, more resiliently, maybe even more kindly?
Definitely something to think about. Well, thanks for joining us on this deep dive. We hope it's given you some new tools and perspectives on the algorithms, both digital and human, that shape our world.